Okay, today we will cover, hopefully I can fully cover 3 sections. Each of these sections are actually quite simple, not too difficult, but it requires a lot of training after class. So please, please, please do yourself a favor that you practice through the suggested homework after class. Okay? Especially this weekend. I really think that's how we utilize this the weekend. Now, you will see that today's lesson is one of the lectures I give that is, in my opinion, is special. Okay, because you don't see this technique of explaining from any textbook. Now, I'm not saying that I'm bragging about it as, hey, you know what, I do things differently. No, I actually learned this myself during my undergraduate study. Okay, I learned this from my professor. Well, my professor basically say, you watch, you study from my lecture first, and then after that, you read your textbook. Okay, you read your textbook, try to do problems from there, and from there you will gain some experience. Okay, okay, give me a second. Now, let's start with cylinders. We covered this a bit last time when we went over section 12.1. Cylinders are defined to be surfaces that is parallel to an axis, or maybe more than one axis. That's how it is being defined. Now, the thing is, we get used to think that cylinders looks like a tube, right? Unfortunately, maybe that's in our daily life, but in our calculus 3, the word cylinders refers to surfaces that is parallel to one of the 3 axes. Okay, now the thing is, how do we identify such surfaces? Now, note, I believe I mentioned this last time. Note, the equation of a cylinder, the equation of a cylinder always miss a variable, maybe more. Now, an example. In one dimension, for example, when we say x equals to 3, in one dimension, basically one number line, x equals 3 is actually just a point on the number line, 3 units to the right of 0. This is in one dimension. Now, in 2 dimension, you basically have, if we have x equals to 3, notice that in 2 dimension, we are missing variable y, right? Okay, what happened then, we basically copy that dot, that point 3, you copy that parallel to the y-axis. Now, all of a sudden, what you see? You see a line, x equals to 3. Okay, so the principle of missing a variable suddenly give us a graph that is parallel to an axis, already implicitly taught even in our algebra. Okay, for example, another one, if we have y equals to -2, if you have a y-axis and this is 0, then that's a point 2 units below 0, right? Okay, that's in 1D, in 1 dimension. Now, however, in 2 dimension, in 2 dimension, you basically copy that point -2, but you copy that along or parallel to x-axis. You copy that parallel to x-axis. So you get y equals to -2 as a line in 2 dimension. So suppose we bring this to 3 dimension. What will x equals to 3 in 3 dimension? Well, we basically copy that in z direction. I think I want to do it this way. So we already have, this is x equals to 3, right? This is x equals to 3. In 2 dimension. But you are still missing z, right? So you copy this line parallel to z. What do you see? You see a plane. And this plane is not just this rectangle. Actually, it is extendable to the left, right, and up and down. Okay? So then you end up with this plane here. This plane x equals to 3. Maybe I draw a rectangle from this point to that point. Okay? This is in 3 dimension. Now, let's do more examples. Suppose, for example, I have y squared plus z squared equals to 4. Notice that this is missing x. So the way we sketch the graph or imagine this, you imagine, oh, okay, let's start with an YC plane. Oops, wrong color. Let's start with YC plane. This is Y, this is Z. Okay, and then in 2 dimension, that is actually a circle with radius 2, right? That's actually a circle with radius 2. Now, what happened in 3 dimension? Well, in 3 dimension, what we do basically, we copy paste this circle parallel to x-axis. So suppose I have, maybe I change color. Suppose I have this circle just like before, right? I copy paste this along x-axis. So now I have this. And to help us with the shape of the circle, I have these dashes here to help us seeing that it is maintained the circular cross section. Okay, this is the x-axis, this is the y-axis, this is the z-axis. Okay, the last example I give you for this, because I went over this last time in, I think, in lecture 1b, lesson 1b. Let's say I have z equals to e to the x. Z equals to e to the x. Notice that this is missing y. Okay, so what I will do is I will graph that on xc plane. Let's say this is x, this is z. Now e to the x, if we sketch that, will look like, let me use another color, maybe a black color, will look like approximately like this. Okay, now the thing is we will copy this along the y-axis. Now, can you imagine if we have this x and c like this, will the y-axis coming to us, coming out from the paper, coming out from the coordinate planes, or going into this xc plane? Now, the answer is it goes into the xc plane. Okay, in other words, if I draw that 3-dimension, where this is the x-axis, this is the y-axis, this is the z-axis, then that curve, or the curve on the YC plane will look like this. On the YC plane. Now the thing is, I will copy paste this thing. I will copy paste this thing along y-axis. Okay, the curve therefore looks like approximately like this. Okay, to accentuate or to emphasize the curve. Like that. Okay, so I hope that explains that it is actually parallel to the y-axis. Okay, now that's about a cylinder. Of course, there are infinitely many graphs you can do. We will never end. You can only practice to get a better view of that. Okay, now that's for the first part on cylinders. The second part, our main focus for this section today, is the quadric surfaces. Why we call that quadric surfaces? Well, because it comes from quadratic forms in 3-dimension. Basically, when we look at the equations has x squared, y squared, and or c squared. That's why we call that quadric surfaces. Now, to explain these surfaces, I will need 2 foundations from your algebra and calculus 2. The first one about what we call translation. So before I really get into quadric surfaces, I will get into some foundational idea first. And the first foundational idea is on what we call translation. I'm sorry, not translation, dilations. Dilations. That's the type of transformation in which we stretch or shrink the graph. Okay, now I try to use examples that you understand first. Okay, and you can kind of like connect, relates to in algebra, and then later on I will jump to calculus. Three things. First one is on unit circle. Idea from unit circle. That is x squared plus y squared equals to 1. You know, unit circle looks like this. It's basically a circle centered at origin with radius 1, right? That one is easy. Okay, that one is easy. What I want to show you is the following. We have circle x squared plus y squared equals to 4. We say this is a circle centered at origin with radius 2. That is correct. That is correct. Nothing wrong with that. That is correct. But I want to teach you a newer way to look at that equation. Okay, a newer way to look at that equation, not to replace what you learned before, but to supplement, to add a new nuance, to add a new flavor into the way you look at an equation. And it is by seeing the following way. If we replace x by x over a, then the graph is stretched by factor of a in x direction. Likewise, for y. Okay, now take a look on this equation. I replace x by x over 2 and the y by y over 2. So notice from this equation, I replace the x by x over 2 and the y by y over 2. What happened then? That unit circle, originally radius 1, now becomes, you stretch in the x direction by factor of 2, you stretch in the y direction by factor of 2, you come up with a circle with radius 2. Okay, now this equation, however, becomes x squared over 4 plus y squared over 4 equals to 1, which is the same to this guy. Okay, now in algebra 2, intermediate algebra or algebra 2, you learn ellipse. Ellipse x squared over a squared plus y squared over b squared equals to 1. And you learn that as an ellipse centered at origin with axis in the x direction a and in the y direction b. Which, if you think about it, it's basically, a unit circle in which you stretch in the x direction by factor of a and in the y direction by factor of b. And because a and b are different, you don't get a circle, you get an ellipse instead. Okay, so that's basically a unit circle. You start from unit circle, stretch by factor of a in x direction, and by factor of b in y direction. Okay, so it's basically in line to what we learned before. Okay, now please don't underestimate this this idea though, the one I actually mark in green, because it is very, very useful even in case that we underestimate before. For example, we know a plane has x-intercept, y-intercept, z-intercept 1, 1, 1. Looks like this. The equation is x squared, x plus y plus c equals to 1. Notice that this is a plane, right? Okay, this is a plane. The x and the y and the c intercepts are all 1. Okay, 1, 0, 0 for x-intercepts, 0, 1, 0 for the y-intercept, and 0, 0, 1 for the z-intercept. Okay, now using that idea, the relation idea, then what kind of surface we have if I have, for example, 3x plus 4y plus 2z equals to 12. Then the way we think is, oh, okay, let's make the other side becomes 1. Therefore, I will divide by 12. Then I get x over 4 plus y over 3 plus z over 6 equals to 1. Now from there, I'm sorry, this should be 3 here, huh? Now from there, we know right away, oh, it's basically this plane here, but I stretch in the x direction by 4 instead of 1, now becomes 4. In the y direction by 3, so instead of 1 now becomes 3. And the c direction instead of 1 now becomes 6. So this is now our plane. Okay, now that's the first foundational idea that we need for these quadratic surfaces. The second foundational idea actually coming from your calculus 2. So it depends on how strong you are in your calculus 2. Which part, Thomas? I need you to get very well with polar coordinate system. Now, first, I want you to learn polar coordinate system in 2 dimension as follows. Polar coordinate system, but we only use the r and z as if they are x and y. As if x, y coordinate system. I know it's kind of strange, but imagine you have a RZ coordinate system okay, instead of XY coordinate system. Now, can you imagine the graph of, Z equals to R squared as the XY coordinate system? Well, Z equals to R squared is basically a parabola. Okay, but what I borrow from polar coordinate system is actually the following. Notice that this Z equals to R squared is missing the theta, which is in our polar coordinate system. What happens if we are missing a variable? It means you copy paste, right? Okay, so in 2-dimension RZ, that's what it looks like. People who just look at my note and don't watch my videos, I think they will get confused. Okay, in 3-dimension, you think of rotating this curve here around the z-axis. Okay, and then you replace your, then that's what it looks like. Okay, now in 3-dimension, then we can call that, let me copy paste that graph. Sorry, I copy paste that graph here, but notice that I change my R, now becomes Y, and then I draw the x-axis here. Now you will see then R squared in polar coordinate system is x squared plus y squared. Okay, so again, it depends on how strong you are in your foundation here. I teach you this earlier so that you can study later on, and yeah, feel free to ask me questions. I myself try to do problems from our textbook to enrich you, but honestly, I cannot go backward too much. In other words, if your foundation in Calc 2 sucks, there's only so much I can do to fix that, but it's not my job. It's your Calc 2 instructor's job. Okay. Now that's the first example. Let's call this the first example for this idea here. Now again, this idea is actually coming from my professors back in Indonesia when I learned Calculus 3. Another example, suppose I have this ellipse, but my ellipse now is using R and Z. So R squared over 4 plus C squared over 9 equals to 1. In 2-dimension RC plane, we call that RC plane, but it's actually just XY plane, but I name it R here, I name it Z here. This will be an ellipse stretch 2 units to the left, right, and 3 units up, down. So this is what it looks like. Okay. Now, because I try to see that in 3-dimension, okay, when I try to see that in 3-dimension, what I do next is I rotate this curve or this ellipse here around z-axis. So then it will look like this. I hope by using these dashes here, you can see the accent, the feeling of the three-dimension view by doing so. Okay, now I copy paste that again. But this time I change my R becomes Y. And this is my x-axis. Okay, if I rewrite that r squared, it is x squared plus y squared over 4 plus c squared over 9 equals to 1, or x squared over 4 plus y squared over 4 plus c squared over 9 equals to 1. That is the equation of that ellipsoid. We call this ellipsoid. Okay, now this guy here is called paraboloid. Now, in case the cross section, when I say cross section, is this part here. In case the cross section is not a circle, but let's say an ellipse, then we call that elliptic paraboloid. Okay. Think about this. Suppose from that example one, let me use red color. I come up with you this way. Z equals to x squared over 4 plus y squared over 9. What will that be? It's basically that paraboloid, right, with a circular shape, but you stretch in the x direction by 2, in the y direction by 3. So what happened then? It looks like approximately like this. So in the y direction is wider. In the x direction is skinnier, not as wide. Okay, let me use some highlight to help us see that. You see, I hope you can feel how it is being stretched in x direction, different from it is being stretched in the y direction. Okay. And of course, we can do a lot more. Another one that I need to introduce to you is, for example, if I have r squared minus c squared equals to 1. So you need to know x squared minus y squared equals to 1, what it looks like. Similar to. Now, if you don't know what x squared minus y squared look like, then you will not know what r squared minus c squared look like. Okay? X squared minus y squared look like hyperbola open in the x direction. Like this. Okay? And it has asymptotes. I hope you remember that. Now, this is x, this is y. Now, what happened in RZ? Well, in RZ it will be basically the same. I copy paste that thing. But now I change this x becomes y. I'm sorry, x becomes r and y becomes z. This is r, this is z. Okay? And then we suddenly spin this around the z-axis. If you spin this around z-axis, then it looks like this. Okay. Now to add flavor to that so that we see the XYZ component, I copy paste that down here, but I change the R becomes, I wonder if you remember, change the R becomes Y, and going in the X direction, that's our X direction. Now the cross section here will be circular. Okay, now we call this hyperboloid from hyperbola, right? Hyperbola that you spin around becomes hyperboloid in one sheet or off one sheet. You see, we call this ellipsoid, comes from ellipse that you spin. Paraboloid comes from parabola that you spin. Okay, here we have hyperboloid in one sheet. How about other sheet time as well? We may have hyperboloid in two sheets. Example 4, if we have z squared minus r squared equals to 1, and it looks like this. Okay, this is our r, this is our z, and then let me make it in black then, and then we spin that around c axis. You now see a hyperboloid in, maybe I do it later. You now see a hyperboloid in two sheets or off two sheets. I'm sorry, should be x. Okay, so the equation then becomes a c squared minus x squared minus y squared equals to 1. The one up here will becomes x squared plus y squared minus c squared equals to 1. Okay, now the last example here is, oops, no, that's not what I copied earlier. Sorry, this is not what I copied earlier. I want to copy this. Copy and then paste. Yeah, but then I change the R becomes Y. This becomes X here. Right? Now this is hyperboloid in two sheet or of two sheet. Okay, now using these two foundational ideas, like the spin from a polar coordinate system and then the dilations, basically the stretch and shrink in our algebra 2 and pre-calculus, I hope that enrich you in seeing how to do quadratic surfaces. There is actually another one type of quadratic surfaces I need to teach you though. Something looks like this. Example 5. It looks like what you call that? It's kind of hard to graph. It looks like this. It looks like this. I wonder if you can imagine this though. It looks like the horse seat, like when you ride a horse, right? Okay, where you have a point where this point is actually the maximum if you travel along this path here. But if you travel along that path, it's actually the minimum. Now the equation looks like, in this case, I believe is x squared minus y squared equals to z plus constant. Let me make sure. This one. No, I think this one is this one is y squared minus c squared. Y squared minus x squared equals to z. If I use this as the reference, this is the c-axis, and this is the y-axis, and this is the x-axis. Now, for this type of surfaces, it's actually easier for us to see if we do the cross-sectional, which our textbook called tracing. What is that? What is tracing, Thomas? Tracing, basically you play with the z, which is the height of the function. Okay, like when c equals to 1, you get y squared minus c squared or minus x squared equals to 1, whose graph looks like this. Okay, now if I try to trace it here, when c equals to 1, when the height is 1, it looks like an ellipse open parallel to the y-axis. This one here. If you see that from above, this is what it looks like, where this is the x-axis, this is the y-axis, and the z-axis is actually coming to us. On the other hand, if our z is negative, if our z is, let's say, -1, that's the same to say x squared minus y squared equals to 1. It looks like this. So below the xy plane, the graph has this cross section. Okay. Now remember I show you one software that I told you to download. Let me show you that here. Give me a second. I hope using this software, then we are able to see that better. The software that I show you, right? Okay. Let's see, y squared minus x squared equals to z. What does it look like? Oops, too fast. Huh? What happened? Hold on. Something not right. It is spinning. That's the thing. Oh, I don't. I don't want the clock to run that fast though. Give me a second. How do I do this? Let me stop sharing first for now. Hold on. I think I may need to download it to my, instead of getting it from my Dropbox thingy. Still like that. I'm sorry. That's not what I want to show though. Maybe let's do this one first then. I hope it works well. Oh, still not. I wonder what happened. I really don't know what happened. Supposed to work well. Okay, let me show you the demo first then. This is the demo of the how to use that software. Yeah, it runs too fast. I'm sorry. It's not supposed to look like that. Maybe my computer's too fast, huh? You can drag. You can trace like earlier. Huh? Only this one? We saw this earlier. What happened? Give me a second. Other demo, maybe full demo. No, that's not what it's supposed to look like. It helps you graph in 2 dimension. It allows you to graph in polar. It allows you to graph parametric equation, which we will see toward the end of today's lesson. It allows you to graph multiple graph in one page. Now the thing is, when it comes to 3 dimension, it doesn't show well. Yeah, seems like it doesn't show that well. I honestly don't know why. Which is the purpose I use this software. Yeah, I need to stop it. So, well, anyway, later on you may want to play with that. Okay? Yeah. I know when I play that without Zoom, it works actually quite well. Now, with those said, let's say we do some problem from our textbook. Let me pick a question. Give me a second. Let me pick a question. And then we kind of like try to put things together. I picked this from our section 12.6 in our textbook. It says use traces to sketch. No, I will not use traces. You can if you want to, but don't need. But we will try to sketch the graph. Okay, we will try to sketch the graph from the equations. Okay, so for example, let's say we look at this guy here. Suppose I just randomly pick a question, number 16. Okay, I have 4x squared plus 9y squared plus z equals to 0. What does that look like? Okay, so let's do some scratch work first. If I get rid of all the coefficients, I actually see x squared plus y squared plus z equals to 0, which basically r squared plus z equals to 0, which means z equals to r squared, negative r squared, whose graph looks like this. We get something, right? Which means if I spin it, it will look like this. Does it make sense now? It is a paraboloid facing down. Now, the thing is, what happened with this 4 and 9, Thomas? Well, that's basically the scaling that make it elliptic paraboloid. I don't like this. Let me make it like this. Okay, so instead of facing up, that paraboloid actually face down. It will open in the x direction wider, and in the y direction narrower. Approximately like this. And let's say this is the skirt of that elliptic paraboloid, but it is facing down, center at origin. Okay, if you want to play it better with better view, so that we can see the better scaling, divide the whole thing by the LCD 36. So I get x squared over 9 plus y squared over 4 equals to negative c over 36. Okay, so that's elliptic paraboloid facing down, center at origin. Okay, how about number 18? Number 18, we have 4x squared minus 16y squared plus c squared equals to 16. Let me collect that x squared and c squared together. And then now I divide by 16. Now the prototype of this, now I go to prototype. This is actually looks like this as the basic shape. And if I call this R, this is R and this is Y, it looks like this. Hold on. X, C, R. But then I will spin along y-axis. So if I redraw it, it may looks like this. I will get rid of the red color later on. It opens, it is, how to say, it is parallel to the y-axis. Okay, now I change this R becomes Z, and this is our X. Okay. Now, if we go back here, notice that we stretch by factor of 4 along z-axis, and then by factor of 2 along x-axis. So this graph will then becomes in the c direction, that will be 4. In the x direction, that will be 2. That's the cross section on xc plane, right? But then it will get larger. Okay. Now that's a little example, but again, you need to practice though, to have a better understanding in this part here. The suggested homework I have for this section, where's my note? The suggested homework from here will be 12.6, number 3 to 8. This is the cylinders. Just to review a bit. Number 11 to 36, and then number 41 to 44. Do the odd numbers, but then if you have more, if you have questions, feel free to ask me. Okay, now that's for 12.6. Now let me go on to the next section, 13.1. I will give you a break very soon, but let's go to 13.1 first. We discuss a little bit before I give you a break. Now, chapter 13 is on factor functions. On section 13.1, it is factor functions and space curve. The foundation for this section actually coming from your parametric equation or parametric functions in Calculus 2. Recall parametric functions or parametric equations in calculus 2. Now, for example, at that time, we have x as a function of t equals to 2t plus 1, and then y as a function of t equals to, let's call that negative 3t minus 2 at that time. Okay, right now we will write that in factor notation rt. Notice that this r is a function of t, but it is also a factor. That's why I've used factor notation on the top of that, which consists of x component as a function of t and the y component as a function of t, which we will rewrite as 2t plus 1, negative 3t minus 2. Okay, another one that we learned before, I believe in Calc 2 at times you ignore the t. We will just write, let's say, x equals to cosine t, and then y equals to sine t. The parametric, that's the parametric equation. So if we write that as a factor function, it will be cosine t sine t, whose graph is actually a unit circle, right? Because x squared plus y squared equals to 1. Okay, now let's expand a little bit from what we learned in Calc 2, just to remind ourselves what we learned there, with some extra transformations. So continue from this example here. Suppose I change that x becomes 2 cosine t, and y becomes 3 sine t. What will that look like? Notice that this is actually the same to say x over 2 equals to cosine t, and y over 3 equals to sine t. Using the idea of transformation we learned before, it actually gives us an ellipse with, from unit circle, you stretch 2 units in the x direction and 3 units in the c direction. Okay, in fact, we know from the past, we actually have the direction of the trajectory. This is when t equals to 0. This is when t equals to pi over 2, right? Right now, you basically have the same thing. This is when t equals to 0. This is when t equals to pi over 2. Okay, but if we write that in a rectangular equation, this is actually x squared over 4 plus y squared over 9 equals to 1. Now, it also worth mentioning that when it comes to parametric functions, we may obtain the same graph with different parameterization. In other words, suppose, let me use another color. Suppose I use, what is good one? Maybe bright blue. Okay. Suppose I change x equals to sine t and y equals to cosine t instead. You will see x squared plus y squared still equals to 1, right? So it will still give us a unit circle. Now the thing is, when t equals to 0, when t equals to x0, that will be 0, y0, that's 1. In other words, when t equals to 0, it's located here. When t equals to pi over 2, it's located here. In other words, if we use that parameterization, we get the same graph. However, the starting point may be different. The direction may be different. Okay? Now, what happened in 3 dimension in Calc 3? We have parameterization in mind. We have a parametric function in mind. Written in vector form. Therefore, we call that vector function. Okay. For example, suppose instead of only 1 dimension, let's make it 3 dimension, where we have cosine t, sine t, and then the c component is 2. Notice that the first 2 components give us a unit circle on xy plane cross section. XY cross section. Instead of using the word plane, let me say XY cross section. But then it is at the height z equals to 2. Then what happened? Let's take a look in 3 dimension. That's not what I want to do though. Why it looks like that right now? This one. Yeah. In 3 dimension, it will be at the height 2 units. I draw that unit circle. Now the thing is that unit circle actually have this direction. You know what? Let me enlarge this. It's easier to see. Okay, this is when the t equals to 0. This is when the t equals to pi over 2. And the trajectory actually going around the c-axis in counterclockwise direction, if we see that from above. Okay. Now, of course, I would like you to play more with this factor function later on. I really wish I can use that software that I show you though. I really wonder why it doesn't work on my computer this time. But let's do some technical stuff first. First, let RT, a factor function RT, be xt, yt, ct. Then, first, limit st approaching a of rt is basically applying the limit condition to each component. Suddenly we have calculus 1, but we need to do it 3 times. Okay, for example, let RT be 1 plus t squared t squared e to the negative t, and then sine t over t. Then what about limit t approaching 0 of RT? That is limit t approaching 0 of 1 plus t squared, limit t goes to 0 of t squared e to the negative t, limit t approaching 0 of sine t over t. Okay, now the first component, I think that's easy. You just plug in t equals to 0, right? We get 1. The second component is not clear though. Okay, it seems like we need to apply L'Hopital rule, but let's just rewrite that first. The third component, I need you to memorize that. Okay, from Calc 1, limit of x going to 0 of sine x over x equals to 1. I do expect you to memorize that though. Okay, blame it on your Calc 1 teacher if you don't memorize that. You should. Now, we have issue with the second component because the y component, because if I apply, actually, no, huh? I don't have issue there because if I plug in 0, I get 0 over 1, huh? So, no, I don't have issue there. So, this will be 1, 0, 1. I thought I need to apply L'Hopital rule, but that's only if we have goes to infinity. Okay, that's for just an example. Just an example on how we what is the limit of a vector function. Basically, you apply that limit to each of the components. You may need to work on the components one by one. Okay. The second part is on continuity. Vector function RT is continuous at t equals to a if the limit as t approaching a of RT is equal to RA. This is basically the definition we have in Calculus 1, but this time we apply that to 3 dimensions, to the x component, to the y component, to the c component. Now, please be aware, what does this mean? This implies, first, the limit need to be exists. The limit exists. And when we say the limit exists, it means all 3 components, x, y, z, exist. Second, not only it exists, they're equal. Okay. We know from Calculus 1, and therefore we can carry that over here, all polynomial, note, all polynomial exponentials and then sine, cosine functions are continuous. on all real numbers. So we don't have issue with continuity, and therefore the limit always exists. Okay, we will have issue later on when we have, for example, rational functions. Okay, but let's continue after the break. Right now it's 5:53. We come back at 6:03. Let's continue. Let's say I pick a question from our textbook. Let me see what question is good. Let's see number 2. This is from 13.1, 12.2, number 2. Number 1, we already have that, right? Okay, so find the domain of this vector function. So for the x component, we have xt equals to t minus 2 over t plus 2. From there, we see the domain is, the domain for xt is all t where t cannot be negative 2, right? The y component, yt, we have that sine t. The domain for sine is all real numbers. And then for the c component, that's ln 9 minus t squared. The domain is all the t where 9 minus t squared has to be strictly positive. That's the domain for logarithm, right? Okay, so when we solve for this inequality, 9 minus t squared, need to solve this. The first step to solve polynomial inequality, we get the critical numbers. We basically set it equals to 0 first. So we get t equals to, you are in Calc 3, so I believe you can do it fast. 3 equals to plus minus 3. Step 2, we do the sine graph. Negative 3 and 3, both of them will give us 0 in the polynomial. But then the graph is actually facing down, so if we do testing points, the signs, the plus minus, will be as follow. Right? So the solution from here, it will be the interval from negative 3 to 3. Now, then what happened to the domain of RT? Putting things together. See, we are okay with between negative 3 to 3, not including the endpoints, but also we need to exclude negative 2, huh? Okay, so we are okay with this interval. So the domain will be from negative 3 to negative 2 union negative 2 to 3. Okay, that's the domain of this factor function. In other words, if the t is outside of this interval, we will get undefined. Now, how about the limit questions? Let's say we have number 6. Find the limit of this factor function. Then attack that one by one. Okay, for the x component, limit t goes to infinity of t e to the negative t. I think I write it way too high. That's the same to limit t goes to infinity of t over e to the t, and then we apply L'Hopital rule. We get t goes to infinity of 1 over e to the t. As t goes to infinity, this goes to 0. For the y component, limit t goes to infinity of t cubed plus t over 2t cubed minus 1. Because t goes to infinity, then I will divide by the highest exponent. Limit t goes to infinity of divided by t cubed. Let me show you what I do. Divide by t cubed on the top, divide by t cubed at the bottom. And we get 1 plus 1 over t squared over 2 minus 1 over t cubed. When t goes to infinity, I will get 1 plus 0 over 2 minus 0, which is 1/2. As for the c component, limit of t goes to infinity of t sine 1 over t. Now we know that sine 1 over t must be between -1 to 1, right? So if I multiply by t, this will be between -t to t. You know what? Let's do it this way instead. We know that sine 1 over t is at most 1, right? So if I multiply by t, the magnitude will be less than equal to absolute of t. Okay, in this case, t is positive though. Now, as t goes to, I cannot, huh? No, I cannot. It turns out that I cannot do it that way. I try to squeeze it, but my t goes to infinity instead. No. I cannot do it this way. I'm sorry. I have to do it another way. I think I will do it. I think I will do it this way. Sine 1 over t over 1 over t, right? But as t goes to infinity, then 1 over t goes to what? Goes to 0 from the right hand side, right? In other words, I can now change this limit. Instead of t goes to infinity, I will say 1 over t goes to 0 from the right hand side of sine 1 over t over 1 over t. Let's call that u for now, just for as a dummy variable. But then I hope you see that we learned this in calculus 1. This is equals to 1. So limit t goes to infinity of that factor function is 0, 1/2, 1. Okay? Now, if you remember the equation of a line that we learned in the previous sections, I think that's 12.5, in our last lesson, that's actually a factor function. Suppose, for example, call this example 1 for this section. I don't know. Just call that another example. Find the factor function of a line containing, let's say, 2, -3, 1, and let's say 5, 4, -2. The way we did it at the time, let our P naught, the initial point, be 2, -3, 1, and then P1 be 5, 4, -2. Okay, so our factor, direction factor, will be P1 minus P naught, right? That will be 3, 7, -3. So our factor function for that line is now 2 plus 3t, -3 plus 7t, 1 minus 3t. I wonder if you remember that, where this, the 2, -3, 1 is my initial point, and my 3, 7, -3 are direction factors. Okay, so the idea of factor function is something we already learned back in 12.5. Now another example, and I think this is worth mentioning. I take this example in the textbook. Okay, find a factor function. I think I use instead of the. Find a factor function of the curve where x squared plus y squared equals 3. Now that is a cylinder, and y plus c equals to, let's say, 2 intersect. You know what? Let me just make that x squared plus y squared equals to 1 for the sake of simplicity. Okay, now what I want to do for now, I will borrow from GeoGebra. Graphing calculator. No, this one. No, this one. I'm sorry. I go to GeoGebra and I will graph that first. This is only to help you visualize that. X squared plus y squared equals 1. That gives us a cylinder, right, with radius 1, parallel to the z-axis. And then we intersect that with another plane, y plus z equals to 2. Okay, you see, this is what it looks like. And the nice thing about this, you can actually play around the view. You see what I mean? Okay, now suppose I screenshot that thing and then post that, put it on my notes here. Of course, I need to make it smaller so that easier to see. The intersection we are talking about is actually this part. Let me use a thicker black color. Maybe it's actually this part here. That's the one we are looking for. Okay, how do we write that path? That's a space curve. It's a curve in 3 dimensions using our factor function. Okay, now one way to do this, it's not always easy. It's not always easy. That's why I need you to practice a lot. One way we can do is, first, in this case, we can see that from above because we have x squared plus y squared equals to 1, right? Okay, so if we see that from above, it is actually a unit circle, right? Can we parameterize this? We can parameterize this using x equals to cosine t and y equals to sine t, right? Okay, now in the second equation, we have is y plus c equals to 2. Therefore, the c is equals to 2 minus y, which if I borrow from there, my c is 2 minus sine t. Now, our factor function is cosine t sine t 2 minus sine t. Okay, and if you want, you actually make the t from 0 to 2 pi, even though actually that's not necessary, because if the t goes from negative infinity to infinity, this curve actually go around and around and around and around and around forever. Okay, but if you limit that from 0 to pi, then it will go only one round. Now, suppose our issue will then be, Thomas, what happened if we don't have that graphing software? Well, the fact is, in your test, you are not supposed to touch your computer, right? So you can only imagine that more by graphing practice. Okay? Oh, no, that's not what I want to do. Sorry. What I want is I want to catch this, copy this, and then paste it here. Suppose I change this. Remember earlier I was originally want to make this equals to 1 was 3, right? So how do we do that? Still, x squared plus y squared equals to 3 means the radius is radical 3, right? So the parameterization in calculus 2 is square root of 3 cosine t square root of 3 sine t. And then y plus c equals to 2 becomes z equals to 2 minus y, and therefore z equals to 2 minus square root of 3 sine t. Now then rt equals to square root of 3 cosine t square root of 3 sine t 2 minus square root of 3 sine t. For t from 0 to 2 pi. Again, if you want to limit that, that it goes only one round. Okay? Now, please listen to me. You need a lot of practice for this. You need a lot of practice for this. Please do the suggested homework. And again, feel free to ask me questions if you have any. Okay, I may not answer you directly, but if you ask me that question before I start working on the supplemental video, I may put your question in there and answer it in there. Okay, now your suggested homework for this section is 1 to 11, 7 to 20, 27, and then 29. Not a lot though, not a lot. I strongly suggest you to try. I will try to find also a software that enable us to graph three-dimensional space curve. I'm honestly surprised that my new calc doesn't work this time. I don't understand why. It works in the past. It works in the past, and I don't know why right now it doesn't work. You know, it seems like it works too fast instead, such that we cannot really see what happens when it which if in slower computer I can show my students what it looks like, but right now I cannot. I don't know why. I need to find out the reason behind that. Maybe because the software I show there is not a complete software, but I will try to find out, or I will try to find out another method, okay, another software to do that. Okay, next one I want to do is 12.7, which is section 12.7, which is cylindrical coordinate system. And then the second part is spherical coordinate system. I honestly feel very strange why the author of our textbook suddenly take this away from the new in the newer edition, while it's actually in the older edition. Now, I have the handout given to you on the discussion board. Okay, please download that. And the suggested homework basically coming from there, as you will see later on. Okay, we start with cylindrical coordinate system. I tried to explain it as much as simple as possible using what you have learned in the past. Now, a cylindrical coordinate system happens to be basically a polar coordinate system extended with z-axis. So we can see this as, you can see this a polar coordinate system. But you know, polar coordinate system is 2-dimension, right? Is 2-dimension plus z-axis. Okay, I hope you can think of it that way. Basically, it is a 3-dimensional coordinate system where on the xy plane, instead of xy and z here, instead of xy, we use r theta. Okay, we use r theta. So instead of xy, we use r theta. Now imagine if you have the following situation. Like this is the radius. Okay, and then this is the theta. Okay, this is the r, and this is the theta. I think I should use another color, huh? This is the theta. And then when you go up, you still use c. So coordinate P here will be expressed as r theta c. Notice that the first two components basically polar coordinate system in xy plane. Okay, so you imagine XY plane now becomes a polar, right? Now you extended it into 3 dimension with additional Z axis. Okay, with that said, what we basically need to review from here is how to convert from polar to rectangular coordinate system and rectangular coordinate system to polar. Okay, if my notation in my class, cylindrical coordinate system will be denoted with subscript C. Okay, R theta Z in cylindrical coordinate system, we will learn to convert to X, Y, Z in rectangular coordinate system. Now, again, like what I said earlier, the first 2 components basically polar convert to Cartesian. Maybe I call that XY plane. Okay. So reviewing, in the past we have, suppose I have X, Y, and a point on X, Y. What will that be in rectangular, in polar coordinate system? What will that be in polar coordinate system, where this is the R and this is the theta? Now, R squared is we know that's equals to X squared plus Y squared. Okay, so R equals to square root of X squared plus Y squared. The thing is, we may have a negative radius though. So I will cross this out and will not use that. Okay, our textbook do agree that even though R comes from the word radius, but when it comes to polar coordinate system, the R may be negative. Okay, next, how about theta? The theta is equivalent, not exactly equal to tangent inverse of y over x. Now, why I say depends on equivalent, we may need to adjust the quadrant. Okay, now the nice thing about cylindrical coordinate system, if we go back to 3-dimension, notice that the C components are the same between cylindrical and rectangular. They are the same. Okay, so we really just need to worry about X, Y, and R theta. Okay, now on the other hand, if we happen to have R and theta, what is X and Y? The X will be R cosine theta, and the Y will be R sine theta. Okay, now let's say for example, call that example 1. Suppose we have 1 comma 3 pi over 4 comma 2 in cylindrical coordinate system. What will that be in rectangular coordinate system? Now, of course, as you remember, the C will be the same, right? C equals to 2. No computation needed. Let's make it -2 instead. Okay, let's make it -2 instead. So c equals to -2. Now, how about the x? The x will be r cosine theta. Now, because that's a special angle, I do expect you to be able to give me the exact value, okay, which is -√2/2. The y is 1, which is the radius, times sine 3 pi over 4, which is positive √2/2. So 1 comma 3 pi over 4 comma -2 equals to -radical 2/2 radical 2/2 for the y, and the c is -2. This is in cylindrical, this is in rectangular. Okay, now how about if we go backward? Let's call this part A, and now we go to part B. How about we go backward? Suppose I have 3, -3, -3, 4 in rectangular coordinate system. What will this be in r theta z in cylindrical coordinate system? Oh, the c will be the same, right? The c equals to 4. The problem is, what is my r? My r will be square root of -3 squared plus -3 squared. That is 3 radical 2. And the theta equals to tangent inverse, equivalent to tangent inverse of the y over the x. That's tangent inverse of 1. That's pi over 4. Now, the problem is, however, we see -3, -3 is located in quadrant 3, right? -3, -3 is in quadrant 3, not quadrant 1. So we need to adjust our theta. Our theta originally pi over 4 here, right? But we need to send it to quadrant 3. So theta equals to 5 pi over 4. Okay? We need to adjust, right? We need to adjust that. So the coordinate -3, -3, 4 in rectangular coordinate system, that is equal to 3 radical 2 for the radius, 5 pi over 4 for the theta, and 4 for the z in cylindrical coordinate system. Okay, now let's see further the reason we learn cylindrical coordinate system. It has a lot to do with what you learn in trigonometry and in calculus 2. Now, for example, sketch the graph of r equals to 4 sine theta. Can we identify that? What is the graph look like? Well, notice that this function here, this equation here, does not have z component, missing z. Right? So this later on will become a cylinder. It's a surface parallel to the z-axis. Okay, which, as long as we can graph the curve in 2 dimensions, we will get the surface in 3 dimensions. So let's graph this in polar first. This is r squared equals to 4r sine theta, which is x squared plus y squared equals to 4y. So x squared plus y squared minus 4y equals to 0. And then I complete the square. I add 4 both sides. I end up with x squared plus y minus 2 squared equals to 4. In 2 dimension, this is a circle centered at 0, 2 with radius 2. It looks like this. Okay? In 2 dimension. But in 3 dimension, it becomes a cylinder. As a cylinder parallel to z-axis. With radius 2. So this is the x in the y-intercept there is 4, 0, 4, 0. Okay, and this is the axis of that cylinder. Okay, now one of the edge here happen to touch the z-axis. Okay, so yes, it has a lot to do with what you know about polar coordinate system. Okay, now I will spend more time here on identifying some important shapes in polar coordinate system. The first one, important shapes in polar, and therefore it becomes important shapes in cylindrical coordinate system. Okay, the first one, when r equals to constant, let's say r equals to 2. R equals to 2, this is a circle centered at origin with radius 2. Okay, in fact, we can work it out this way. R equals to 2, therefore r squared equals to 2, therefore x squared plus y squared equals, I'm sorry, r squared equals to 4, therefore x squared plus y squared equals to 4. In 2 dimension. So in 3 dimension, it will still be a cylinder. Okay, second, how about if the theta equals to constant? Let's say theta equals to pi over 3. Theta equals to pi over 3. Now we know that tangent theta equals to tangent pi over 3. But tangent theta is y over x. And tangent pi over 3 is radical 3. Therefore, y equals to radical 3x. Okay. In 2 dimension, this is a line through the origin passing through the origin with slope m equals to radical 3. But what happened in 3 dimension? In 3D, then it looks like Let's try to sketch that. So this is our x, this is our y. The slope is radical 3. So maybe it looks like this, right? Where the angle here is pi over 3. Okay, but then you notice that this is actually a line, right? This is actually a line. I wonder what I should do to make it dashes. How do I make it dashes? There's no way. I will figure out later time. But then if I copy in the z direction, it will give us a plane, right? In 3D is a plane. This guy here in the first part in 3D is a cylinder. To be more precise, circular cylinder. It's a cylinder whose cross section is a circle. Okay, now the thing is, we have more than this though. For example, one thing we learned earlier about r equals to 4 sine theta. Okay, this is actually in 2D. This is a circle centered at 0, 2 with radius 2, right? Okay, how about if we have cosine? 4 cosine theta. You will see, you try to play with the way I did it here. Okay, that will be in 2D, that will be a circle centered at 2, 0 with radius 2. Now you may want to try experiment with maybe instead of 4, you replace that with -6 and play with the equations, see what then it looks like in 2D, and therefore you will be able to see what it looks like in 3D. Okay, another one may be useful. Actually, no, it will be useful because we see this a lot later on. How about z equals to r? This is what is, how about c equals to r? Or z equals to r squared. Now, I did explain this when we did quadric surfaces. So this will be helpful if you know this. Notice that in 3 dimension, these two equations here actually missing the theta, right? So it's basically when we graph r equals to z, when we graph r equals to c in 2 dimension using RC, this is r and this is c, it is actually this line here. It's actually this line. Okay, now the thing is, what you need to do then is you rotate that with respect to y-axis. And you will get a cone. To be more precise, it's actually a bicone. Okay. How do you get that, Thomas? Well, because c squared equals to r squared and that makes it c squared equals to x squared plus y squared. As we learned before, that's actually a cone. Okay, and the one we have here, it originally looks like y equals to r squared, so it is actually a parabola, right? This is actually a parabola. This is r, this is c, but then in 3 dimension you basically spin that around the z-axis. Okay, so actually think of it this way. Suppose I have c equals to, let's say, sine r, right? In 2 dimension it looks like this, right? Now rotate this. If you rotate this, it looks like, but this time it is in 3 dimension. Of course, you have some peak here, and then you have some valley here underneath. Just imagine that what happened with that curve if you rotate that around the z-axis. Okay, you graph that first on RZ plane, and then you rotate around z-axis. Okay, now let me go on to the next part, a more difficult part, spherical coordinate system. Spherical coordinate system is built based on cylindrical coordinate system. So it is impossible for you to understand spherical coordinate system without first understanding cylindrical coordinate system, which is impossible to understand if you don't learn polar coordinate system properly. So for you to learn spherical coordinate system, before that, you need to learn cylindrical coordinate system. Before that, you need to be good with your polar coordinate system. Okay, let's first show you what a spherical coordinate system look like. Let me steal from my handout. Give me a second. I wonder where is my handout. I already have that earlier. Hold on, give me a second. Spherical coordinate system looks like this. I steal this from the handout, by the way. So what happened is spherical coordinate system consists of 3 components, and the second component theta is the same to what we have in polar. The first component, however, is rho, which is the direct distance from origin to the point. We call that rho to distinguish that from r radius. Rho is the radius in 3 dimensions, the direct distance. Now you will see toward the end later on why we call this spherical coordinate system, because it is very nice to describe a surface or coordinate or a figure that is spherical in nature. Okay, now this is the rho, basically the direct distance from origin to the point P. The theta is the angle from YC plane to that point. I'm sorry, from XC plane to the point. And the phi is the angle from positive C axis. The phi is from positive Z axis. Now, from that figure, I hope we can derive some important formulas. Give me a second. My children's too loud, sorry. Now, you will see at least like rho is actually the direct distance. Suppose you have coordinate P in X, Y, Z here. Then your rho will be the square root of X squared plus Y squared plus Z squared. Okay. Your theta, just like in polar, that's equivalent to tangent inverse of y over x. Your phi, however, is cosine inverse. You will see the reason why we use cosine inverse instead. It's because you will see that theta actually moved from 0 to 2 pi, right? Theta is actually from 0 to 2 pi to make it one round. But the phi actually moved from 0 to pi only. Okay, in fact, the phi will be in the first quadrant if it is above the xy plane. It will be, the phi will be greater than pi over 2 if it is below xy plane. Let me help by sketching. Imagine if you have a point below the xy plane. So let's say this is the rho, right? The angle will be from positive C axis, go down there, pass through pass through the xy plane. Maybe if I draw it from a bit to the sides. Go below. Now notice that the angle here is more than 90 degrees, right? Now, if we graph that further, let me erase this one. So what is phi then? This phi we can see as the cosine inverse, that's the C over rho. That's the cosine inverse of Z over rho. Okay, because rho is always positive. That's the nice thing about spherical coordinate system. The rho always positive. Okay, the rho always positive, and therefore the value of cosine inverse of C over rho depends on the C being positive or being negative. If the C is positive, then the phi will be in the first quadrant. If the Z is negative, then the angle phi will be in the second quadrant. Okay. Of course, we can also use another method. For example, from this picture here, you can see this is basically R in our polar coordinate system. Right? This is R here. Okay, so we can say this is equivalent to tangent inverse of R over C. Okay, just be careful that in this case we want to keep the R being positive, while we know from calculus 2 polar coordinate system may have R being negative. Okay. Now I will stop here. On Monday I will continue on this spherical coordinate system. We will do conversion from spherical to polar. I'm sorry, from spherical to rectangular, spherical to cylindrical, cylindrical to spherical, and then rectangular to spherical. Okay, I will stop here and see you on Monday.